Hello, hello. Welcome back, everyone. So next up, we have another fantastic talk I'm really excited about. And our speaker, our guest speaker, hello.
Hello, Miranda.
How are you doing, Mario?
I'm fine, thank you. How about you?
Oh, I'm doing well. Thank you so much for joining us today and talking to us about handling time series workloads in industrial IoT. Yeah, this is awesome. And Mario Ishikawa is the CTO of PackIOT. So yeah, go. Please take the floor.
Okay, let me share my screen here. Okay, is that okay? Okay. So I'm going to talk here about IIoT, which is Industrial IoT. This is the summary. So my name is Mari Ishikawa. I am the co-founder and CTO of PackIOT. I started my career as with a technical degree in electronics, and then I moved to information systems, which is similar to computer science. So I consider myself an IIoT engineer specialized in software. I have been working for over 23 years with industrial software for industrial automation in manufacturing plants and power companies. I am passionate about collecting and organizing data, and I'm the CTO at PackIOT. Just a little about PackIOT. It's a software startup for manufacturing companies. It was founded 3 years ago. And what we do, basically, we help the manufacturers to understand their performance, how the production is performing. We are bringing affordable and scalable big data analytics for manufacturing. We have offices in Brazil and in Europe and customers all over the world. So, what's IIoT? And Miranda, feel free to interrupt me at any time, okay? It can be a conversation also. So, IIoT stands for Industrial Internet of Things. So you can think of IoT, but applied to industries. Any kind of industry, such as manufacturing, smart cities, power plants, power companies. So not only manufacturing. And also we can say is the merge of OT, which is operational technology, this technology applied to the shop floor, with IT. So here's just some examples of devices we see in this environment. This is called a PLC, it's a programmable logical computer. Usually in the past, this kind of device, which is a controller, you can think like a Arduino, for example. It can understand the sensors and it can process their information to give feedback to the system to, for example, to control a machine. But nowadays they are getting much more powerful. They are having like computing powers. And some of them you can install like a Linux, run some edge computing there for example, machine learning. And then you can do several interesting things that are changing now in the manufacturing industry. So how important is time series in IIoT? Similar to IoT. And so basically, if you're thinking IoT, collecting data from sensors in your house, in IIoT is basically the same thing. You have machine, so you can monitor the health of the machine, things like the vibration of the machine, temperature, or can also be regarding the production of this machine, like good counts and bad counts. And where does IIoT, where does it make sense? Where is it applied? So manufacturing plants, power plants, substations, oil and gas, other infrastructures like tunnels and bridges, because they need to monitor the air, the temperature. Airports has a lot of data, a lot of IIoT data. So think of the conveyor belts, if they are running or not, if they should be running and they are not, why. distribution centers like Amazon warehouses. So Amazon warehouse, you have all those robots moving around the place, and all this data is collected, where they are going, what did they get. So this is IIoT data. And what's different? Well, there are some special needs, unlike simply IoT, in which maybe you don't need the real-time feedback. In the shop floor, in power companies, you really need real-time data or near real-time data. Near real-time data would be like if you're monitoring the production, and it doesn't matter for you if it comes late, like 10, 30 seconds later. Also, it's very important, the availability and security. So unlike the IoT on your house, that if you tell if you tell your system to turn on the lights, if it doesn't work, you're going to be sad. But in the manufacturing or in a power plant, this can be disastrous.
A little more important, yeah.
Yeah. Calculation of counters. So counters, as you guys that work with time series know, it's a different kind of variable. It's not something that you can simply do an average, max and minimum. So you have to keep handling when the counter was reset or not, and things like that. Also, there is also always context. So for example, when you're talking about a count, so let's say production, if I say that the production is 10,000, I must be always referring to some context, like 10,000 when, in this shift, in this day, or the last shift, or on this current work order. So there's always a context applied. And as any business, there's the data model. So for example, for manufacturing, it's very common, this data model ISA 95, in which you have the enterprise. Each enterprise might have sites, think of plants. Each plant has areas, and each area has lines, production lines. The lines are divided in machines, and each machine has its set of sensors, its controllers, and this is how you can model the data. It also uses specific protocols that are there for over 20 years to communicate with this kind of specific equipments. And one challenge is also that there are many legacy equipment. So those PLCs, for example, they can last for like 30 years without stopping, without breaking. They are really robust. But you will also find some machines that don't even have any kind of interface, so you can connect your computer to start extracting data. Also, there is a lot of use of real-time functions. So what do I mean with this? For example, I am collecting data, and at the same time, I'm applying a linear regression. So this is very common. So here, what's Industry 3.0? Where were we until now? So Industry 3.0 is about automation. So automation of the process. Think like we have 5 machines, one computer that operator is using to see what's happening with these machines, to interact with them. So that PLC that I mentioned, there is a PLC in each machine. But we have this automation. The machines are automated, but part of this data is time series historian, and part is going to this computer, and from the computer, part of this data is going to the historian. So since there were not so many actors, as the network was growing, it tends to get confused. And then Industry 4.0, what is it? In Industry 4.0, it's no longer about the machine running on its own and a controlled and automated process. It's much more about taking advantage of this data to transform it in information, important KPIs, so you can improve your process. In this sense, for example, we need a better organized data flow. So if in the past we used it to see a time series database as the central unity in the network, nowadays what we need is a central unit that can handle the flow of real-time data, which is what also called unified namespace. And this is much more scalable. So you think if you add another computer with another different app that also needs the information from this machine 4, you won't create like a second or a third connection to the machine 4. Once you have this actor here, you have something scalable. So you can add here and just connect to the unified namespace. Any client, anything connected to the unified namespace can work as a publisher or a subscriber. So one thing important here is the MQTT protocol, because it's lightweight, it's going to be efficient for the network, but is also is also going to allow this to be scalable, and it's also open. But we still can have a central database historian, and this kind of software is usually specific for manufacturing or specific on power plants. But nowadays, you might also want you might be worried about the edge connection. So you want to send the data to the cloud, to a data lake, and then you can run machine learning algorithms. So all of this can be connected to this unified namespace. Okay, but what changed? Why are we talking here about also Timescale? Well, again, going back here, if in the past I mentioned the central part of this network was a database, nowadays this database can still be here with its specific functions, but since actually data is disk size is not a problem, any actor here, any web application, any application can have its own historian as a microservice. So, for this case, it's very useful to use, for example, Timescale, because instead of having to buy a new license of a specific historian, you can. It would take maybe months to justify in your company, and you can start right away with something that's open source, is available there, and will cover many of the functions you need. And what is good on Timescale? Well, some things on Timescale are really great to use on Industrial IoT, which is the native compression. The native compression, since the data doesn't change so often, especially when we are talking like things about temperature, and counters also. Counters, for example, if the machine is stopped and we are working with report by exception, which means we are only sending data when there's something relevant, this is already saving a lot of space. But native compression, I've seen in some tests, we save like 10 times the space. Continuous aggregates is a very interesting tool, especially when you don't need actually data. You can use like data normalized by minute or by 10 minutes. And by normalizing, you also apply more context, getting data together that came in different timestamps. But with that, you're going to need, of course, the time bucket and time bucket gap fill. And very interesting are these functions here, the logf. So let's say if you are monitoring the state of machine and the temperature, and the machine is running. So it started running at 1 o'clock, and at 1:30 it was still running, and the temperature was 50 degrees. At 2 a.m. the machine was still running, and the temperature was 65 degrees. So the temperature is changing, but the state not. So if you want to analyze these two variables in a chart, for example, you can use the logf to repeat the unique value that was stored there in this table. Or for example, if you don't collect so often the temperature, and you have like 10 degrees at 1 hour and 20 degrees at 1:10, 1 hour and 10 minutes, you can interpolate to generate the points in the gap. So it will do a simple linear function to create these missing gaps, the 11, 12, 13, 14. Retention policy is also very important in this market because database tend to grow, of course, and the fact that Timescale creates the partition is already very important because you don't lose performance on inserts, on the queries. But sometimes you need to delete things, and just using the delete command, it's very intensive for the server. It will create a lot of log. It will take a long time. So with the retention policy, simply get rid of the old partitions. And here are some numbers that if you want to see more in depth, there is the preview presentation that I did with Timescale, and this was much more detailed. Here is just the summary of this presentation. Here's some examples. I was comparing narrow tables with wide tables and JSON, and narrow table tended to show a better performance for the use case. So here I was showing some benchmarks here. So for data from 10 sensors in a month, a vanilla table, which means a table that was not a hyper table, took around 900 milliseconds on the first run and the second run. I did 2 runs because of the cache and the RAM memory. A hyper table took like 100 milliseconds on the first, around the same time in the second, so much faster. The compressed it was slightly slower, but still comparable, 141 milliseconds. In the second run, it showed that took advantage of the cache. Continuous aggregate, that was a little bit interesting to observe. It took almost 1 second, but it's still a good time. In the second run, it took much less, and showing that it used the cache. But also we have to be open to try new things. For example, this compressed aggregated table aggregating by 10 minutes. What's that? That's not something that exists exactly on Timescale. So I created my own aggregation, not a continuous aggregate, over a hyper table compressed. And then the results are impressive here. Just 13 milliseconds on the first and 2 milliseconds on the second run. And here's some numbers here on disk size. So the vanilla was 10 gigabytes, the hyper table 15. The index took a big part of it. The compressed around 1.2 gigabytes. The continuous aggregate 2.6. And the compressed one, it's impressive, 183 megabytes. I like very much this approach to create my own hyper tables with my own aggregations and compressing them. And I like to use continuous aggregates when I have data that can change with some frequency, and I don't want to handle that like with a materialized view having to refresh this data. So from these tests also, the conclusions is there's no one size fits all. So these are just examples from a specific use case. The index also, it's very important, the choice of index, if you're to use multi-tenant architectures or not. And what I would say also, always try native compression, try to see what's going to happen, how it's going to perform on your use case. Be open-minded to try your own aggregation. Like I said, I like to do that. And also create views that can mix compressed table, like old data, with continuous aggregates, fresh data. This is something I also do quite often. So I create views with all the data that is compressed or aggregated in with a bigger granularity, and connecting to fresh data, let's say recent data, with a better precision, and using the right SQL, using the right view, we can have a very good performance.
That's awesome. Thank you so much for sharing with us, Mario. And I do have some questions. So why would people still use other IoT specific databases nowadays?
Well, there are some things, for example, first of all is modeling. And so this specific IIoT database, they handle this modeling of your data. So let's say you have every machine has two compressors, every compressor has some variables. It's quite easy for you to do this in this specific database, and especially handling calculations. So let's suppose you have some variables that you actually don't have, you are not collecting, but it's a property on your model, and it's calculated as an expression deriving from other variables. So you can do it much easier and with less time if that's your case.
Cool. And what do you feel like has been the hard part of using Timescale with IIoT? I know that you mentioned some of that in the talk, but maybe some more on that.
Yes. Well, one of the hard parts is comparing to some other tools. Some other tools for IIoT, we usually have the collector. So it will collect the data, bring it to their database, and they also have also this modeling that I mentioned. And they will also have, for example, some real-time functions, which now I see them being used on hyperfunctions, and I hope it grows the catalog. But for example, one thing that up until some months ago, it was not possible to do it in Timescale, but it was possible to do in this database. Let's say you have like production in this model, and one other variable is the linear regression of this production. So you can extract this easily navigating on a tree view, pull the linear regression and put like on your chart. Now there is some things with hyperfunctions on Timescale, but just for you to have an idea, there are several functions that are useful to the industries, to power companies, to manufacturing, and you can save a lot of time.
Awesome. Yeah, the hyper functions, as we add them, I feel like it's cool to see how it's kind of solving more and more problems that people have. And I know I actually have one question on, because I saw that you mentioned counters, and I was curious if you have seen or looked at any of our counter ag. It's a newer, it was one of the hyper functions that we released, like from experimental to like full-fledged hyperfunction. Have you looked? I was just curious if you had seen it at all, or if that solves any of your problems. If not, I mean, that's no problem. I was just curious.
Yes, no, I saw it. Yeah, but since we are already solving this in a different way for some time, it was not. I wasn't not going to change it, but I saw, and also in the past, some people from Timescale helped me to work on the efficiency of these counters, and also because one of the biggest pains is really, for example, when the counter resets. So if you're just using the delta and you have to consider if it's resetted, it's a little bit more difficult. But with the function, I believe it's much easier.
Very cool. And then one more question, at least for me. Hopefully, maybe users also have questions. But so how to model the database when you don't know beforehand how many or which sensors you're going to monitor? How would you go kind of about that?
Okay. This question is interesting because if you know beforehand, you would probably use a white table with each sensor, each property that you are monitoring as a column. But when you don't know beforehand, usually one of the approaches is to use the narrow table, in which instead of just timestamp and value, it's the timestamp, the key, and the value. And so you would need another table to have the information which one is this key, or using also JSONB. You could use JSONB if you need to test to see if the performance is going to be good, and also if you want to use native compression or continuous aggregates, if it's going to work for your case, which one is going to be better.
Awesome. And I think we do have one question And I know that we're running out of time. I think it's basically break time, but I'll throw one of them up here, and then maybe the second question, if you want to reach out in Slack, because Mario, you're in our Slack. I'm sure that you'd be happy to look at, or talk to folks. But one of the questions is, are you feeding the TimescaleDB over OPC-UA pub sub MQTT? OPC-UA doesn't look like it was designed for time series data. That was one of the questions.
Okay. Yeah, OPC-UA is a standard protocol for connecting several different machines and computer systems. And it works great in the shop floor. So we use OPC-UA to collect the data from the machine. But to send to Timescale, we don't use OPC-UA because I believe to move to the cloud, MQTT is more efficient. So to connect to the machine, we use whichever protocol it works. So for example, OPC-UA. But to send to the data, then we have a pub sub system also in the cloud on PackIOT, and essentially we're using MQTT with encryption.
Very cool. Yeah, thank you so much. I think we will wrap up here for just a quick break before our last talk of the day. Mario, thank you so much for coming onto the show with us and sharing your awesome insight. Yeah.